Hi, grade 10s. Mr. McLeod here with our last unit, trigonometry. All right, the topic for today is something called similar triangles. The word similar in math has a very specific meaning. So, two triangles are similar if they have the exact same shape, but they don't necessarily have to be the same size. So, one triangle could be bigger or smaller, but they have the same shape. So that means that the corresponding angles in both triangles are equal. So if you, for example, grew the smaller one, it would overlap exactly the bigger one, so that all the triangles have the same three angles. And this also gives the triangles the property that their side lengths are proportional. So, for example, if you have two similar triangles and you have one side is twice as long as the same side in the other triangle, then all of the sides in the bigger triangle are twice as big. And we're going to use this property to help us find side lengths of unknown sides in triangles. And we do this by setting up the ratios of corresponding sides. Okay, let's get into this. So these two triangles, BCD and EFG, are similar, and that's what this kind of curly thing means. Which means that they're the same. They have the same angles, but just one triangle is bigger than the other. Okay, so we have to imagine if you were to grow the smaller triangle, for example, and just to imagine which angles match up between the two triangles. So in this case here, angle B is the biggest angle in this smaller triangle, and that's going to correspond to this angle E. So angle B is going to be equal to angle E because those two angles are corresponding angles. And also this angle D is the smallest angle in this triangle, so it must correspond to this smallest angle in the bigger triangle, which is G. So angle D is equal to angle G, and then the last angles are going to correspond as well. So angle C corresponds with angle F. Angle F. All right, so a lot of times the two triangles will not be in the same orientation, so you have to imagine in your mind kind of rotating one of the triangles so that they match up. All right, now let's pick out the corresponding sides. So for example, this longest side in the smaller triangle is CD. CD. And we're going to make a ratio, and just making a ratio just means to divide the two side lengths. So CD in this triangle matches up with this side here, FG. FG. And whatever that number is, it's equal to the ratio of two other pairs of corresponding sides. So let's pick out the smallest side in this smaller triangle. So this side is BC. BC. And the corresponding side is EF in the bigger triangle. EF. And then that leaves this last side, which is BD. And this last side here, EG. So because the side lengths are proportional, that means that when you divide pairs of corresponding sides, that all those numbers are equal. And this is what's going to help us find the measures of missing sides in triangles, which is useful for solving problems. One more note too, it doesn't matter which order, but what you want to do is if you are putting the side lengths of the smaller triangle on top, then you should do that for all the ratios. Or you could put the side lengths of the bigger triangle on top, but just be consistent with how you're setting up your ratios. So either you're always putting the smaller sides on top or the bigger sides on top. Okay, now we're going to use this idea to find the measures of these unknown sides. So what we do is we find the pairs of corresponding sides that we know, for which we know both numbers. So, for example, we know that this BC corresponds to this EF. So we know this measure is 4 centimeters, and we know that this measure is 5 centimeters. So I'm going to use BC over EF, and we're going to set that up with one of the other ratios, CD over FG. Okay, now in the diagram, BC is equal to 4 centimeters and EF is equal to 5. So we go 4 over 5, and CD is our unknown side, which is length of B, which corresponds to this side, FG, which is 10. So we're going to have on the other side B over 10. Now in this case, it's easy to see the multiplication relationship here, that this bottom side is twice as much as this bottom side here. But you might get a little bit more difficult and challenging numbers. So what it always is going to work is something called cross multiplying. So we know that when you multiply the top of one fraction times the bottom of another fraction, that equals the bottom of the first fraction times the top of the second fraction. All right, so I usually like to have my variables on the left side. So I'm going to do is go 5 times B. 5 times B equals 4 times 10. And I kind of just like to write it out first. And then I'm going to isolate the B by dividing both sides by 5. I like setting up this calculation like this first, so that I only have to grab my calculator once, and I go 4 times 10, of course, which is 40, divided by 5 is 8. So B is 8 centimeters. And then we can do a similar thing for the other side. So we start with a ratio of two sides for which we know both measures. So in this case, BC and EF, we know both measures. And then we set that equal to another ratio of corresponding sides. So this is the one we didn't do yet. BD and EG. Okay, let's move on to using that idea of finding a missing side to solve some real world problems. So here we go. A tree casts a shadow of 18 meters along the ground, of course. And at the same time, we put a meter stick sticking straight up out of the ground and measure that shadow as 0.75 meters. So find the height of the tree. So what we always want to do is first draw a diagram. So I'm going to quickly draw a diagram here. Okay, so here's my diagram of my tree, and there's my meter stick sticking up. And what we want to do is take the values from the question and put them in. Uh, we see that we have kind of two triangles. This makes two triangles, and so we assume that all of the rays coming from the sun are coming at the same angle. So these two triangles are similar, but just the one triangle is much bigger than the smaller triangle. So the tree shadow is 18 meters. And of course, if we were to measure the shadow, we would measure along the ground. So we know this side of this triangle is 18 meters. And the shadow of the meter stick is 0.75 meters. So that means this side is 0.75 meters. And of course, a meter stick is 1 meter long. So this side is 1 meter. And we're trying to find the height of the tree. So the height of the tree would be this side of this triangle. So I'm going to put that as an x. All right, now we can use our idea of corresponding sides to solve for this missing side x. This shadow bottom side, of course, corresponds with this side here. So there's my first ratio, 18 over 0.75. And then since I did the big triangle first, I'm going to do this side here in the big triangle, x, which is x, over this side in the smaller triangle, which is the 1 meter. So we have x over 1 meter. And then we solve by cross multiplying. So we have 0.75 times x is 0.75x. And 18 times 1 is just 18. And we divide both sides by 0.75. All right, 18 divided by 0.75 is 24. It's 24 meters tall. The tree is 24 meters tall. Okay, let's look at one more. The width of a river can be calculated using only measurements taken on one side of the river as shown in the diagram. So first off, how do we know that the triangles are similar? Well, if we can show that two pairs of corresponding angles are equal, then we know that all the corresponding angles are equal, and then therefore the triangles are similar. So in the diagram, we're told that this is a right angle in this smaller triangle. That must correspond with this right angle in the bigger triangle. And also, if you remember from your angle theorems from last year, when you have two straight lines that intersect, you create what's called opposite angles, and we know that opposite angles are equal. So these two angles are equal, those must correspond as well. We have two pairs of corresponding angles are equal, therefore the triangles are similar. Okay, now let's find out how wide the river here. The diagram is drawn for us. We have to just pick out what sides are correspond to which sides in the other triangle. So if these two angles are corresponding, that means that this angle up here in the bigger triangle corresponds with this angle down here in the smaller triangle. So how would you orient these triangles so they match up? And to me, it looks like we should rotate this bigger triangle around, which means that this 24 meters corresponds with this side, which is 8.5 meters. And then this unknown W side corresponds with this side, which is 14.7. So maybe I'll just do the calculations up here so I don't have to move the page down. Again, I like to just write down the entire calculation. That way I'm only picking up my calculator once and I can kind of do this calculation all at once. Okay, and I got a value for W is 41.5 meters, about. So I can answer the question. All right, I want to point out something really, really interesting. If you're paying attention, you might have noticed that all of these measurements are on one side of the river. So this is such a practical way of measuring something. We didn't have to cross the river in order to measure how wide the river is. We could have made all of these measurements on one side of the river. And that's really neat from a practical standpoint. We didn't actually have to physically cross the river to go to measure the width of it. Similarly, with the tree example, we didn't have to physically climb the tree to measure the height of the tree. We just measured along the ground how long the shadow was, which is a very practical and simple thing to do. And from that, we were able to determine the height of the tree. So this is actually a really powerful idea. And imagine um, how this could apply to measuring distances to objects that we can't physically get to, like stars. So astronomers actually use this idea to measure the distances to stars that are relatively close to us. Because the Earth moves around the sun in its orbit, stars that are very, very far away don't appear to move very much. But stars that are close, as the Earth moves around the sun, the angle of that star in relation to stars that are really, really far away, it changes very, very slightly. And actually, astronomers have a measure, or use this as a measure to stars. It's called a parsec. So a parsec is the distance a star has to be for the angle of that star to change by what's known as an arc second. And that's a very, very small fraction of a degree, a very small fraction of a degree, which is 1/3600th of a degree. So astronomers are able to measure the angle that this star appears to move and use that to calculate the distance to that star, because if we know the angle, we also know the distance from the Earth to the Sun, and we can figure out very accurately how far away that star is. All right, that's it for now. Hope you guys have a great weekend. We'll talk to you next week. Bye.